Welcome. In this video, I will be changing things up a little bit, and I'll be explaining a topic rather than doing a proof. And the topic is going to be functions. I'm going to be trying to explain this in the most general terms possible without any reference to limited analogies to machinery. Okay. So what a function really is, or at least a class of objects that can be considered functions, is a relation between two objects. And in this case, the two objects are going to be these books and these colored circles. All right? You can do this in any way you like. You can connect Stuart to yellow. But looking at this book, there's absolutely no reason to do this. But you can do it. There's nothing stopping you from making that relation, making that function. I'm a bit of a physicist, so I do not want to make useless functions. All right. So what I'm going to do is I'm actually going to make something that's slightly useful, and I'm going to say, well, I'm going to look at the spine of these books, and I'm going to relate each book to the color that's most highly represented on the spine. Okay. And if you look at these three first books, they all are mostly blue by design. I put the blue books together, and then I draw a common line to the blue circle. I do the same thing with the green books. I draw a line to the green circle. Same with yellow. Oh shoot. Oh, this is yellow. Never mind. The color's a little bit weird on this blackboard. And then I take the last two books and I draw them to red. That's it. I made my first function. Isn't that beautifully simple? That's it. It really is it. We're missing a lot of interesting structures because we're doing this so generally, but this is what a function is, okay? And I'm going to call this function f. I'm going to write f down here to represent these relations. All right, so this is one way to do this function. And if I want to, so I started by doing a verbal representation of this function, which is just to say blue, the color of the spine, okay? Then I do this visual representation, and then I can also do like an algebraic representation. And I can do that like this. I can go f of st, and st stands for Stuart, is equal to blue. All right, so these are three different representations of this. All right, so let's make another function. This function, some of your teachers might not like, especially in upper secondary education, but this is a critical, I feel, class of functions for the study of functions, all right? And you might not even meet these functions again, or this class of functions again, until you're at university doing complex analysis, where they're pretty critical to the analysis, all right? So I'm going to make another function, and I'm going to call it g, represented by green lines, okay? And what I'm going to do is I'm going to look at all the colors in these books, and I'm going to draw a line to those colors, okay? The first Stuart here is arguably both purple, blue, and red. The next one is, I would say, only blue and red. Third one, mostly blue. Some gold, but gold is not an option, so I can't do that. Green and red. Green, red. Ooh, blue, yellow, and green. Oh, I drew this in the wrong way. This one should have gone here. Boom, boom. This one goes blue, green, and yellow. The caramel is mostly green, slightly monochromatic. Yellow and blue. Blue and yellow. Three books that are all only yellow. And then two books that are mostly red. That's another function. All right? And the question is, well, what is g of Stuart? Well, g of Stuart is now three values. It's both blue, purple, and red. And I'm going to represent that this way. I'm going to go, it's purple, it's blue, and it's red. It's a multi-valued function. And people don't really like that on first approach. It's essential later on, but for now, people just don't like this class of functions. But I will argue in a second that these are actually pretty essential to the whole analysis. Yes, another thing here is that, side note is that I want to represent the size of this, the number of these values with these vertical lines. These vertical lines are usually used in math for some kind of size of objects. So it's the size of this set, the number of values. And in this case, the size of this is 3. All right, beautiful. Okay, so far, I've been looking at this as a slightly symmetric object. I can turn this whole thing on its head, and it's still totally valid. All right. But now I'm going to start looking at this directionally, and I've actually already been doing that. I've been taking f of the books and getting some value in the colors. All right. And so to break this symmetry, I am going to call the books, I'm going to call the domain, and then I'm going to call this the codomain. And they have this domain, both have this domain in its name because there is still some symmetry here. It's just a slight break of the symmetry. I'll call this B for books, and I'll call this C for colors. Okay. Now I want to see what happens if I flip this on its head with this direction in mind. Okay. So if I follow this orange line down, I'm following this F relation, but it's different because this blue value color goes to 3 books. All right, so this other way of going is called the inverse of f, and it's notated like this. So it's f to the power of -1, and then I write in the value of the color. And what do I get? Well, I get Stewart, I get Hatcher, and I get Griffiths. I get a multi-valued function, even though I started with a nice f here that was not multi-valued. The inverse is multi-valued. So these multi-valued functions show up immediately, even if I try to avoid them, in the inverse. All right. What I can do now is I can take this function and its inverse and put them together. I can compose them, right? And I do it like this. So if I take the f and I compose it with its inverse, what happens is I start by taking the inverse, which is to say I start from the colors, I go down to the books, and I go back up to the colors. So what I'm actually doing, I'm going from the colors to itself. All right? And what this function does, it takes a color and it makes it into, actually it's easiest to just take an example. So f of the inverse of blue, for example, it's going to be f of this set here, Stewart, Hatcher, Griffiths. And when I take a function on a set like this, I just take it on each individual element. And what I get here is, I get the color of these 3 books, but the color of these 3 books is exactly blue. So I started with blue, and I ended with blue. And that is the relationship between the function and inverse. If we take them on, if we use them on each other, then we get back what we started with. All right. Let's take the other construction. Let's do this the other way around. So we take f to the minus 1, and we compose it with f. Okay? So this goes from, oh, sorry, not from C. This goes from B into B. From the books to the books. And if I take the values of a single book, we take Stewart. Well, it's the inverse of blue, which we already showed is this set. So I start with Stewart, but I get all its pals, all its color pals. Okay, so I had this nice structure up here where I started with blue and I ended with blue, but here I start with Stewart and I get 3 values back. This is why people don't like multi-valued functions, because they break this, this property that you get the same thing back that you put in when you use a function on its inverse. All right, so let's check out what is then the requirement to have this nice property that we get the same thing back here. Okay. So there are 3 properties that are required to have this nice quality. Surjectivity, all right. So the surjectivity means that each color up here has a line to it. We have to hit all the colors, all right? And in that sense, F is not surjective, but G is surjective because there's a green line to each color, but not an orange line. We could remove purple and make F surjective, but then we're kind of ruining G because we're removing one of its colors, and that's not nice, all right? The second property is injectivity. And injectivity is the property that each color up here only has one line going to it, at most. So we cannot have 2 green lines going to it. That means that it's not injective anymore. All right? So, in this case, F is not injective, and neither is G. All right. And it was actually mostly this property that ruined the fact that we did not get the same thing back when we used the function and its inverse on each other. All right. Okay. We couldn't really fix surjectivity, and it's even harder to fix injectivity, because if I want to fix injectivity, I need to remove some of these lines. That means removing books. But we're looking at these, we want to analyze these books. It's bad to remove books, all right? So we don't want to do that. So injectivity is usually is a more restrictive condition than surjectivity. You can often fix surjectivity, but it's harder to fix injectivity. But let's do it anyway. So I'm going to remove some of these books. I'm going to stop considering them a part of our domain. These, and this one's actually beautiful. Let's just keep that. There we go. There we go. Like that. Okay. Now what we have is we have Griffiths here, so we can remove this this thing here. We only have one line now here down to Griffiths. Same thing here. We only have one orange line going to green. And same thing here, we only have one orange line going to yellow. And we only have one orange line going to red. Beautiful. Now our function f is injective. Let's see what happens to green. We've removed purple. So this is not there. We removed these two. We removed these two. We removed these two. We removed this one and this one. Yeah. basically this last one we kept. And we removed all but the last of the reds. We've also made G injective because most of these books are mostly monochromatic. Okay, so now we fixed both F's injectivity problems and we fixed G's injectivity problems. The only problem now is that F is not surjective. But look what happened when we disconnected this. This color became completely superfluous. So we can just disregard purple. We can remove it from our codomain. We don't regard it anymore. And then F becomes surjective. Right? And all in all, what we have when we have functions that are both surjective and injective, we call them bijective. Right? And bijective have this beautiful property that we had earlier actually, that the only way to get blue is to use Griffiths, and the only way to get Griffiths is to get blue. So these two things are just completely iron locked. These things are pretty much the same object now. So blue is Griffiths, green is the Carmo, yellow is Beltoft and Thompson, and red is Kaplinsky. Right? And this has this nice property that now always, when we compose these things, we take the inverse and the function and we compose them in either way. We always get the so-called identity. And what the identity does is nothing. You give it something and it spits the same thing out again. And this only applies to bijections. That's why many people will require bijectivity for us to even consider the inverse. All right? What I say is we always have the inverse. It just looks nice when the function is bijective. All right? And incidentally, bijections also mean that now, since we have a bijections from the book to the colors, we know that the number of colors is actually the same as the number of books, which is to say, the size of C is equal to the size of B because we can find an bijection between them. This is the most general way to consider functions and define them. It's got slightly complicated at the very end here, but just go back to the start of the video and remember, we created a function and you were all with me. All these further structures are just to be able to analyze these objects in a more systematic and slightly more nuanced way. Okay? So just start from the beginning and see if you can kind of slowly digest the rest of this if this does not make immediate sense to you. Okay? In the next video, I will be narrowing our perspective a little bit and start looking at how we can actually apply this to something like probability theory. Okay? If you have any comments or questions, leave them below.